Welcome to The Explainer. I am so thrilled to have you here today. You can think of this session as your very own one-on-one pre-flight briefing. Today, we're going to master an absolutely crucial lesson on low-speed aircraft handling, slow flight, and stall avoidance. Let's get right into it.
Okay, let's really dive into this. Have you ever wondered what happens when flying slower actually requires more engine power? I mean, it sounds totally counterintuitive, right? It's kind of like having to step harder on the gas pedal in your car just to drive slower. But this fascinating quirk of aviation physics is very real, and it literally lies at the absolute heart of our flight lesson today.
Section 1. Welcome to the cockpit. Preparing for slow flight.
All right, for the next few minutes, we are transitioning from mere passengers to active pilots. Our primary goal here is to completely demystify the mechanics of flying near stalling speed. You see, slow flight is essentially the ultimate awareness exercise. In aviation, we define this as flight below the best endurance speed. And by doing this, we're intentionally exploring a really sensitive zone where any further increase in your pitch attitude is going to result in a stall. So this isn't just an exercise in staring at your gauges, it's a true test of your physical coordination and your intuitive feel for the aircraft.
Moving on to Section 2, Behind the Power Curve, a matter of drag.
Now, before we actually feel this in the air, let's take a quick look at the whiteboard theory. Notice that red swooping line right there? That represents the power required to overcome drag at different speeds. Now, what's really interesting about this slide is if you look closely at the far left side, that shaded area clearly marked slow flight. In normal cruising flight, obviously flying faster requires more power. But on this back end of the power curve, as you slow down, you actually need significantly more power just to maintain a steady speed. So why does this happen? Well, it's because flying at these incredibly low speeds requires a very high angle of attack just to produce enough lift to keep you in the air. And that massively increases what we call induced drag. So, to overcome that huge drag penalty and keep flying straight and level, you basically have to push that throttle in.
Let's contrast these two very different aerodynamic regimes. In the normal flight range, the airplane is inherently speed stable. It's wonderfully self-correcting. Like, if a random gust of wind slightly increases your speed, the drag naturally increases, which then automatically slows you right back down to your trim speed. Easy, right? But look at the slow flight range. It is entirely unstable. If a gust causes you to lose just a few knots of airspeed here, your total drag actually increases, which slows the airplane down even further. No joke, the airplane absolutely will not fix this for you. As the pilot in command, you have to actively take corrective action by promptly adding power or slightly lowering the nose.
Section 3. The feel of slow flight. Inside the cockpit.
Okay, let's shift away from the whiteboard and talk about the actual sensory experience. The very first thing you're going to notice in your hands is what flight instructors call sloppy controls. Because the aircraft is moving so much slower through the air, there is vastly reduced airflow, and therefore reduced air loads over your wings and tail. Your yoke is going to feel remarkably less firm, and you'll suddenly find you need to make surprisingly large, sweeping movements just to get the airplane to do what you want. But there is one major exception to this. Your elevator and rudder will actually still feel somewhat snappy and responsive. Why? Because they're continuously bathed in the high-speed air being blasted backward from your spinning propeller, the propeller slipstream.
Next up, we really have to prepare for something called adverse aileron yaw. Here's the deal. When you turn the yoke to roll into a turn, the downward deflecting aileron on the outside of the turn creates way more drag than the upward deflecting one on the inside. This drag imbalance twists or yaws the nose of the airplane stubbornly in the exact opposite direction of your intended turn. And at the lower airspeeds and high angles of attack we see in slow flight, this adverse yaw is highly pronounced. So to keep the aircraft flying smoothly and balanced, you must actively and assertively apply rudder pressure in the exact same direction as your aileron input. It's an absolute must.
All right, imagine your hands resting firmly on the yoke in this left seat. Notice just how far back the control column has to be positioned to keep that nose pitched so high against the horizon. If you didn't remember to retrim the aircraft prior to slowing down, man, you are going to be fighting a very heavy, fatiguing pull force in your forearms. The natural stability of the airplane desperately wants to pitch the nose down to get back to its original trimmed angle of attack. You literally have to physically force the machine to maintain this slow, nose-high attitude.
Section 4. Mastering the maneuvers, the PAT formula. Now that we really know how the airplane feels, let's build some muscle memory. So the crucial point is mastering this exact sequence to establish slow flight safely. Step 1.
Reduce your power and progressively raise the nose to maintain your current altitude. Step 2. Patiently wait as the airspeed bleeds off to your desired target. Step 3. Right as you hit that target speed, you must significantly increase your power to keep the plane from sinking. And finally, Step 4. Rapidly retrim to relieve that heavy control pressure and balance the aircraft with your rudder. Remember, you're going to need to make relatively large, bold throttle movements here compared to anything you do in normal cruising flight. Whether you're smoothly climbing, gently descending, or holding strict level flight at these low speeds, you absolutely must internalize the fundamental aviation mantra shown here. Power plus attitude equals performance, meaning your resulting flight path and speed. So, if you want to climb from slow flight, you increase power, slowly increase your attitude, and trim. We call it PAT. If you need to descend, you reduce power, gently adjust your pitch attitude, and trim. Honestly, everything up here is just a carefully coordinated dance of power and pitch.
And throughout all of this really delicate maneuvering, you absolutely cannot forget the golden rule of balance in a single-engine prop plane. High power plus low airspeed equals right rudder. That high power setting sends a powerful, spiraling slipstream of air crashing directly into the left side of your tail, which is constantly trying to force the nose of the plane to the left. You have to actively and firmly hold right rudder pressure to keep that little black balance ball perfectly centered in your turn coordinator. Never forget the right rudder.
Section 5. Avoiding the stall, recognizing the edge.
Okay, we are now intentionally taking the aircraft right up to its physical limits. Let's move to VI and see how these symptoms build in the cockpit as you bring the control column further and further back. First, you'll clearly notice the decreasing airspeed on the dial, accompanied by a distinct drop in the aerodynamic noise level. It seriously gets eerily quiet outside your window. Next, your controls will feel incredibly sloppy and almost completely unresponsive. Your arms are going to be fighting an intense, high pull force on the yoke. Then, suddenly, the shrill stall warning horn or buzzer is going to start blaring in your headset. And finally, you'll feel the pre-stall buffet. This is an unmistakable physical shudder vibrating right through the airframe and into your seat, essentially screaming that the wing is about to stop flying.
Once you feel those severe symptoms, and of course after ensuring the airspace around you is totally clear using your standard Hazel checks, it's time for the immediate relief of the recovery steps. At the absolute first sign of that imminent stall, your instant reaction must be to release the back pressure on the yoke. Simply let the nose drop. Simultaneously cram in full power to arrest your descent, aggressively level the wings with coordinated rudder and aileron, and just let the airplane safely accelerate back to a normal flying speed before you gently pull up to climb away. It's a lifesaver. And this brilliantly illustrates the most empowering and absolute rule in all of aviation. A stall only occurs when the wing is physically forced to exceed its critical angle of attack. The wing absolutely will not stall if that back pressure on the control column is removed. Remember, you are the pilot in command. By simply relaxing your grip and allowing the nose to lower, you instantly remove the threat of a stall. Keep that in mind, trust the physics, and you'll always stay safely in control. But it does beg the question, now that you've mastered the slow end of the airspeed indicator, what other aerodynamic limits are you ready to conquer next?